Okay, so we're going to talk about topics 3.11 and 3.12 in this video. So topic 3.11 is about spectroscopy in the electromagnetic spectrum. So the questions are going to ask you to explain the relationship between a region of the electromagnetic spectrum and the types of molecular or electronic transitions associated with that region. So we are first going to start by reviewing electromagnetic radiation, and I'm going to move my little box down just a little bit. There we go. So electromagnetic radiation is attributed to James Clerk Maxwell in 1864. So what he created was a mathematical theory of light. And his theory said that light and other radiation works in terms of wave-like electric and magnetic fields. So we're talking about light as waves when we're talking about the electromagnetic spectrum. So when we talk about electromagnetic radiation, there are a couple of properties or aspects that we think about. First is wavelength. The symbol that we use for wavelength is the lowercase Greek letter lambda. And the wavelength is the distance between a given point on a wave and the corresponding point on the next cycle. So oftentimes we think of wavelength as the distance between two peaks or two valleys. And it's measured in length just like anything else. If waves were long enough that we could measure them with a ruler, you can, and some waves are. A lot of times when we're talking about wavelength, we're talking about wavelength in the realm of nanometers, but we are talking about length. The next aspect is frequency. The symbol for frequency is the lowercase Greek letter nu. Looks kind of like a V, but it's not. It's kind of got a little curve to it. And frequency is the number of waves that pass a given point in some unit of time. So it's how often they cycle. Okay, so a higher frequency means they cycle faster. Lower frequency means they cycle less fast. In frequency, the units are inverse seconds. So you'll see it sometimes as s to the negative 1, which is the same as 1 over s, or it's 1 hertz. And the speed of light in a vacuum, symbolized by the letter C, is equal to the wavelength times the frequency. So we're going to use that constant as a way to go back and forth between wavelength and frequency when we go to do some calculations. So let's look at the actual spectrum. I'm going to drop my little box down here. Okay, so our spectrum ranges from radio waves to gamma rays. So our radio waves have a very long wavelength, very low frequency. So the longer the wavelength, the lower the frequency. Because there's more distance, so that means it's going to take longer for them to cycle through a full wave cycle. Radio waves are measured in the realm of 1 meter to 10 to the third meters. Okay, so these are nice long waves. These are things we could actually measure if we could see them. As we move across our spectrum to shorter wavelength, we're going to get a higher frequency and therefore higher energy. So we go from radio to micro to infrared. There's a very short spectrum, or a very short piece of the spectrum that's visible light, so that's what we can see. And then ultraviolet. So I always remember that as infrared is going to be on the red side of the visible spectrum, which is the lower energy side. The ultraviolet is going to be on the violet end of the visible spectrum, which is the higher energy end. So that's how I know which end caps. So infrared, visible, ultraviolet. Then it goes to X-rays, and then it goes to gamma rays. And so as you move across the electromagnetic spectrum, your wavelength is getting shorter, your energy is going up, and your frequency is going up. So let's look at how some of these things are related to different types of transitions. So we talk about this in terms of photon energy. So photons are light as particles, and so difference in the absorption or emission in different spectral regions. So microwaves so lower energy cause molecular rotation. So they're going to rotate around the bonds. Infrared, so a little bit higher, is going to make them vibrate. And visible light into UV light causes electronic energy levels to change. So that's where the electrons are actually changing the energy levels. So that means you need higher energy to cause changes in where the electrons are located to excite them into higher energy levels. The lower energy, which is microwave, is just going to cause them to rotate. and in the infrared region, it's just going to cause them to vibrate back and forth. So this is just something you have to have memorized. You need to know that this is what's going to happen in each of these ranges. So if we look at this in a kind of graphic picture form, so as you increase your wavelength, you're going to increase your energy, although this shows decreasing energy, but we all know increasing is the opposite of decreasing. Okay, so we've got rotation, then vibration, then electronic excitation, so that's where the electrons are going to move, and then the next one past that is bond breaking and ionization. So that's where you're actually causing, there's enough energy to break those bonds and to cause electrons to leave, and so that's where you form ions. So that's kind of the next step beyond. But normally, up until now, we've just talked about adding energy and they break bonds, or you add energy and you lose electrons. But there's actually some other things that happen first. We see them rotate, we see them vibrate, then the electrons move, and then we have enough energy for the bonds to break and the elements, the atoms to ionize. Okay, so let's talk about the photoelectric effect. That's topic 3.12, which is to explain the properties of an absorbed or emitted photon in relationship to an electronic transition in an atom or molecule. So this is where we're going to get to some actual calculations for this. So the photoelectric effect is attributed to Max Planck in 1900. So energy is quantized. So this is where we're looking, we're getting towards the idea of light as particles. And so Planck said that energy, only certain energies were allowed or possible. That's what it means by quantized. So it's not a fluid range. It's going from this point to this point, and the in-between is not allowed. And the equation that we're going to look at here is E, which is energy, is equal to H, which is Planck's constant, because that's what happens when you're a fancy scientist. You hopefully get something named after you. It's more likely if you're a white guy, but hopefully you get something named after you if you're a fancy scientist. So energy is equal to Planck's constant times nu. And nu, since that is the frequency, we already know that that is the speed of light in a vacuum divided by lambda. So we can combine those two things together to relate energy to wavelength using two constants, Planck's constant and the speed of light in a vacuum. With Planck comes in Einstein. So Einstein said that electrons are ejected when light hits metal only if the frequency is high enough. So this goes along with what we saw before in our electromagnetic spectrum. So you need enough energy in order to spit out an electron. So we can look at that, and we can look at the electrons that are spit out of a piece of metal, and then we can do some calculations backwards to determine the energy of the light that hit it. And so what comes into play here is that light is also functioning as particles, not just waves. So there's light has kind of a two-part. It can act as a wave, it can act as a particle. When we talk about light as particles, we talk about photons. That's what we call them. They're the little packets of energy we call photons. So we're going to use these equations to manipulate these variables, go back and forth between them. These are calculations. Some you'll have to do in your head, some you'll be able to use a calculator for. The equations are given to you on your equation sheet with your periodic table, and you get the constants, so that's not anything that you have to have memorized. The key here is being able to read the question and figure out what information you're given, and then figuring out how to manipulate the equations and interpret your final answer. So again, these aren't equations you have to have memorized. You should recognize when you need to use them. You don't have to have the constants memorized. Those will be given to you as well. But again, it's all about recognition and knowing, like, hey, when I'm talking about photons and energy and colors of light, things like that, these are the equations that I'm going to use. So that's a brief summary of the electromagnetic spectrum and the photoelectric effect.